Nutrient cycling in both lakes and streams occurs in the aquatic phase, but streams, being flowing systems, have unique aspects to their nutrient cycles. Carbon and nutrients spiral down streams and rivers and the groundwater beneath them. And here, the authors use the word spiral, and that's really an important factor for thinking about the differences between lakes and streams and their nutrient cycling. So if we take a look at a headwater stream, for example, and this is the headwater stream of the Allegheny River, you can see that it flows relatively quickly. It's a narrow stream, and then this one's relatively open also, so that a lot of light hits it. The nutrient cycling that happens in a stream like this is a little bit different than what happens in a relatively large river like the Missouri River. Often with stream and river systems, we'll talk about nutrient spirals as much as cycles. But for the most part, if you ignore vertical displacement, nutrients still cycle. There are different pools, and nutrients go from one pool to another, and then back to the initial pool, and there are still inputs, and there are still outputs from that system. But because water is flowing, we tend to think of the nutrient cycle as happening more or less in a spiral. So if this is one pool up here and another pool down here, you'll have a situation where it's going to move in one phase and then down to the other phase and then up to the other phase. So it's cycling as it's moving, and that generates a spiral. So if you have to think of this visually, think of this as a slinky, and there's different degrees of stretching of the slinky depending on the system. Now there's two different terms that we're going to use to describe the cycle. The first one is going to be turnover length, which is the downstream distance moved when an element is in organic form. So think of organic form as having been taken up by a plant, for example, and we want to know how far downstream it's going to move while it's in a plant. The other term is uptake length. And essentially, uptake length is the average distance that a given nutrient is going to travel after it's been released. So if this is going to be within a plant, and this is going to be inorganic phase, we're going to have a certain distance that it travels within the plant, and that's the turnover length. And then we're going to have another distance that represents the uptake length, which is the average distance after it's been released. And then it's going to spiral back into the plant phase, and then the inorganic phase. Now for a headwater stream, an average spiral going from plant to inorganic might be somewhere on the order of 200 meters. Of those 200 meters, a given nutrient is going to travel before it's taken up again. Most of that is in the mineralized phase. So the plant phase tends to be relatively short, and the mineralized phase tends to be relatively long. So when we think about differences in turnovers and spirals within streams, up to 85% of the stream length within most drainage networks is actually in a headwater system. So in that case, we really need to think about the headwater systems and what their spirals are like: turnover length, uptake length. So again, we have turnover lengths and uptake lengths. And that turnover length is how far a given nutrient is going to travel when it's after it's been taken up by a plant, for example. And then we have the uptake length, which is how far it travels when it's in an inorganic phase, ammonium or nitrate. So the turnover length is often relatively short in a headwater stream because it's been taken up not necessarily by phytoplankton that's going to be moving downstream, but instead a plant that's going to be sitting and attached. And so these can often be relatively short. The turnover length, the uptake length, is going to depend on a number of factors, but it increases exponentially with differences in stream discharge. So for ammonium, we can get 10 to 1,000 meters of average distance traveled once nitrogen has been released into the water as ammonium. Whether it's just 10 meters or 100 meters or 1,000 meters really depends on flow. So if we have relatively low stream discharges, so not a lot of water moving through a system, it's going to give you a relatively low uptake length. And it's the large systems that have a lot of stream discharge where ammonium, once it becomes available, travels a long distance. The reason why this is important is that uptake length is essentially a multiplier. If you have a short uptake length, that means your spiral is going to be relatively short. And a given amount of nutrient in that system is going to be used to generate productivity multiple times, compared to having a long uptake length, where most of the time that nutrient is going to be in an inorganic phase in the water, and only rarely does it get taken up. So short uptake lengths mean that nutrient is going to be multiplied in its effect on productivity. If we look at differences in concentrations of nitrogen and phosphorus in streams, just like we did for lakes, we'll see again that there are big differences. Those systems that primarily drain forests, for example, have relatively low concentrations of nitrogen and low concentrations of phosphorus. On the other hand, if it's draining agricultural systems, you're going to have relatively high concentrations of nitrogen and high concentrations of phosphorus. Here the black bar represents the inorganic phase and the white bar the organic phase. So what proportion of the nitrogen is inorganic to organic? And that part isn't as important to think about as much as how much nitrogen and how much phosphorus is present in those waters. So as we go from a relatively intact system with lots of productivity, not a lot of nitrogen or phosphorus in the waters draining those systems, by the time we're into an area that drains primarily agricultural systems, a lot of nitrogen, a lot of phosphorus. Streams are important for nutrient cycling, not only thinking about what the uptake length and turnover length are, for example, but also what happens to nitrogen. And on average, somewhere on the order of 75% of the nitrogen that enters into the waters and spirals through eventually is lost as a gaseous form, some kind of oxide of nitrogen or dinitrogen gas. And this is denitrification. So in a lot of systems, they're really important for taking nitrogen out of the water. And yes, it's taken up and fuels productivity, but still a lot of that nitrogen is lost. In addition to reducing the amount of nitrogen that's present in those waters over time, phosphorus also becomes trapped in sediments. So in general, if we have a stream that's working our way through a landscape, and there's going to be inputs of nitrogen and inputs of phosphorus into the system, that the nitrogen and phosphorus that comes out of that system is a lot less than what went into it. The reason for that is we have denitrification of nitrogen, and then we have phosphorus being trapped in sediments and often being redisplaced onto the landscape during floods, for example. So although by the time you get to the end of the Mississippi, for example, there's a lot of nitrogen and a lot of phosphorus, the specifics of the nutrient cycles within streams and rivers reduces the amount of nitrogen and reduces the amount of phosphorus that eventually is lost at the end of the river.